Hello. In this video we're going to talk about Chapter 15, Lecture 12. We're going to focus on the first three learning objectives. We're going to look at a reaction quotient, then use that reaction quotient to determine which direction a reaction needs to proceed in order to achieve equilibrium. Then we will look at ice tables to use an equilibrium constant to calculate equilibrium concentrations, and then we're going to use what's called a BCA table that we're going to use to determine stoichiometry for non-equilibrium reactions. This last point will not be on this test, but we will look at it further for our next test. Okay, so first let's look at what's called the reaction quotient. Reaction quotient is Q, so we've got the letter Q representing reaction quotient, and when we're talking about the reaction quotient, we're comparing it to our K, our equilibrium constant. So let's think about K in general. So K is equal to the concentration of products over the concentration of reactants. Or, of course, it could be pressure of products over pressure of reactants. But we think about K, we think about if K is greater than 1, our top part of our ratio is greater. So the reaction favors the products. And then if our K is less than 1, our reaction favors the reactants, because now we have the denominator being a larger term. And then if K is roughly equal to 1, which almost never happens, but that means the reaction favors neither the reactants nor the products. So we look at K in that way, but when we're looking at K versus Q, we're going to look at the size of Q versus the size of K. So our reaction quotient when compared to our K can tell us what direction we need to proceed in order to reach equilibrium. Okay, so we're not really so much looking at what side of the reaction we favor. We're looking at, in comparison to our K, what do we still need to do in order to reach equilibrium. So we calculate Q the same way we calculate K. We just use initial concentrations instead, or pressures. Instead of equilibrium ones. So we're going to compare Q versus K. If Q is less than K, then our K value has greater amount of products than our Q value does, so we need to form more products. If our Q value is greater than K, then our products are too great, or our reactants are not enough. So we need to form more reactants. And then, of course, if Q is equal to K, we are at equilibrium. So let's look at how we would use this. So we've got the following reaction. NO plus Br2 goes to NOBr. So if we were to solve for Kp for this, we'd have NOBr squared divided by NO squared times by Br2 squared, or Br2. Now, with that, we would get a Kp of 116.6 if we were at equilibrium. Let's see what happens with these pressures if we are not. Oh, sorry, these are pressures. So if we don't have equilibrium pressures, if we have just random pressures, let's see what we get. So we're going to solve for our Qp instead here. We have our NOBr pressure at 0.969 atmospheres. That'll be squared. We're going to divide that by our NO pressure, 0.105, and that's also squared, and then by our Br pressure, 0.400 atmospheres. When we solve for that, we get a Qp value of 212.9. So our Qp value would be greater than our Kp value of 116, which means we need to shift towards our reactants. Our problem right now is we have too many products. Our Qp is larger than our Kp. Okay, now let's look at using our Rice table to determine equilibrium concentrations using initial concentrations and our equilibrium constant. So in order to do this, we need the following information. We're of course going to need a balanced equation. Anytime you see an equation, make sure you balance it. And then the equilibrium expression. So once you balance your equation, you'll be able to figure out your equilibrium expression. You'll need the value of your equilibrium constant, initial quantities of each species. So initial quantities in molarity or pressures in atmospheres of each species. It's fine if some of them are 0, and you need to know which direction the reaction is going to proceed in. If you don't, by looking at the equation, use your Q. So you may need to use Q if you have some of each substance. So if you have no zeros as your initial concentrations, you're going to have to solve for Q. Okay, so after you have this information, you can go through and you can make out your ice table. So you'll make your ice table, or make your rice table, where you're going to have your balanced equation at the top, and then your initial concentrations will go in there, and then you'll also have your equilibrium expression as well. And then you're going to go through, after you determine which direction you're going to shift, you're going to determine which direction, and then you're going to place in basically the change. So you're going to determine the change using the variable x. To show how you go from initial concentrations to equilibrium. Okay. As a note, take into account stoichiometry. It's very important when you're doing your change that you know that the stoichiometry is going to be important. Then you're going to solve for your change. So you're going to add together your initial row, your change row to get your equilibrium row. And then you're going to solve for k. Sorry, solve for x using your equilibrium expression. And your equilibrium row. And the last thing you want to do is check your work. Okay, so it's easiest just to try an example. So we've got the following reaction, H2 plus I2 goes to 2HI. It has a Kp value of 53.5. So that's going to go into our ICE table or our RICE table. And when we do that, we now will need to put in our initial concentrations. Oh, first check and make sure this is in fact a balanced equation. So we can write out our Kp expression. Okay. Next we want to see what initial concentrations we have, and the only initial, in this case, pressure that we have, and actually let's write this in terms of pressure. So this would be partial pressure of HI squared divided by the partial pressure of H2 times by the partial pressure of I2. Okay. So here we start out with a partial pressure of 2.5 atmospheres for HI, but that's the only thing we start out with. So we start out with zeros here and here. So in order to reach equilibrium, we have to go from products to reactants. So we're going to do minus 2x here, plus x, plus x. So our equilibrium row would be x, x, 2.5 minus 2x. We'll then put those equilibrium concentrations into our Kp expression, and we'll put our Kp value in there as well. So our Kp, 53.5, will be equal to our HI concentration, 2.50 minus 2x, and that'll be squared, or sorry, pressure, and then divided by our x's. Okay, what we get is 53.5 is equal to 2.50 minus 2x squared divided by x squared. And what we could do is we could take the square root of both sides. So when we do that, we take our 53.5, we take the square root of it, we get 7.31 is equal to 2.50 minus 2x divided by x. And then we can start rearranging, multiplying both sides by x. We get 7.31x is equal to 2.50 minus 2x. Then we're going to combine our x's. So we get 9.31x is equal to 2.50. And then we're going to divide both sides by 9.31. And we get x is equal to 0.269. That will then go into x for each of these. So H2 and I2 are both equal to, pressures. Partial pressure of H2 and the partial pressure of I2 are both equal to x, so they're both equal to 0.69 atmospheres. And then our partial pressure of HI is equal to 2.50 minus 2x, which equals 2.50 minus 2 times by 0.269, which gives us 1.96 atmospheres for our partial pressure of HI. We of course can then solve for that, see if we get the correct answer by putting it back into our Kp expression. So we take 1.96 and square it, divided by 0.269 squared, and we get a value of 53.1, which is pretty close. So I'd say we did a pretty good job. Okay. We could also do what's called a small x approximation. And with our small x approximation, we're looking at when we have a Kc value that's very small, which means that our x, or change, is not going to be very large, so we consider it negligible. So we'd say when an equilibrium process has a very small K value, so usually we're talking about less than 1.0 times 10 to the negative 4. You can basically, when you're reaching equilibrium, the change x is so small, we consider it negligible. So we can kind of just ignore it whenever it's added or subtracted. So specifically added or subtracted. We still use it when it's multiplied. Still keep when it is multiplied or divided. And the idea is if you subtract a small number from a large number, it's not going to make a big deal, or add a small number to a large number, it's not going to make much of a difference. But if you multiply or divide by a small number, it's going to make a significant difference. So what you're usually going to be looking at is you're going to take your x value, divide it by your initial concentration of whatever your substance is, and you're going to times that by 100%. And if this equals, or if this value right here is less than 5%, then it's a valid approximation. Okay, so let's try an example where we can use the smallest approximation. Here we have a very small Kc, 1.0 times 10 to the negative 5, for the following reaction. N2 plus O2 goes to 2NO. When we start out, there was initially 0.20 molar O2 and 0.80 molar N2 and 0 concentration of our NO. Going to equilibrium, minus x here, plus 2x. We get 0.80 minus x, 0.20 minus x, and then 2x here. And then our Kc expression for this is NO squared divided by N2 times by O2. So we'll put in our Kc expression, 1.0 times 10 to the negative 5 is equal to 2x squared divided by 0.80 minus x times by 0.20 minus x. Here we're going to do a small x approximation. So any x that is added or subtracted we're going to remove. And that's because we have a very small Kc value. So what we're going to get is 1.0 times 10 to the negative 5 is equal to 4x squared divided by 0.80 times by 0.20. And then let's do some math. We get 1.0 times 10 to the negative 5 is equal to 4x squared divided by 0.64. And then we're going to multiply both sides by 0.64, which gives us 6.4 times 10 to the negative 6 is equal to 4x squared. And then we're going to divide that value by 4 and then take the square root of it. And we get x is equal to 1.26 times 10 to the negative 3. To make sure that that is a valid approximation, we take our 1.26 times 10 to the negative 3, divide it by our initial concentration. We're going to take the smaller one, 0.20. And when we do that, and multiply by 100, when we do that we get 0.63%. So we'd say that that's a valid approximation. And then we can then solve for our concentrations of each. So our N2 and O2 concentrations don't change. So our N2 concentration is still 0.80. Our O2 concentration is 0.20, but our NO concentration would be equal to 2 times by X, which would give us an NO concentration of 2.53 times 10 to the negative 3. Okay. Let's just real quick go over BCA tables. So our BCA tables are going to be tables that are used like a rice table, but they're for stoichiometry. So we need a one-way arrow, or one-way reaction, no equilibriums. And then this uses moles, not molarity. And then BCA stands for before, change, and after. Okay, so same idea, you're going to write your balanced equation. Okay, then you're going to put in your initial moles. Okay, then you're going to put those into your B. Okay, so make sure that you have everything in moles, so you might need to convert. Because everything needs to be in moles. Okay, then you'll calculate your change. Okay, using mole ratios. And then you'll calculate your after. As a note, you will generally have to kind of decide your limiting reagent, and if that doesn't give you the correct answer, you have to try again. So we'll start out with the following reaction. So we've got aluminum reacting with iodine to produce aluminum iodide. So we have 2Al plus 3I2. One-way arrow goes to 2AlI3. When we start out, we have 0.50 moles of aluminum and 0.72 moles of iodine and 0 moles of aluminum iodide. So here we're just going to guess which one of these is used up first. Okay, so we're just going to guess, okay, this is the correct one, whatever it happens to be. So I'm going to assume aluminum is my limiting reagent. And let's see what happens. So if I assume aluminum is my limiting reagent, I'd say 0.50 or minus 0.50. And then here I do minus 0.50 times by my molar ratio. So my molar ratio here, we have 3 moles of iodine, 2 moles of aluminum. So it would be 3 on the top, 2 on the bottom. And then same idea here with the aluminum iodide. We're going to add here, but it's going to be 0.50 times by my molar ratio. There's 2 moles of aluminum iodide on the top, 2 moles of aluminum on the bottom. So I would multiply it that way. And what we get is a 0 here. 0.72 minus 0.5 times by 3/2 gives us negative 0.03. And then we get 0.50 here. So because this is negative, I chose incorrect. So we know that our aluminum isn't our limiting reagent, it's in fact our iodine. So let's try this again. So now, we're going to assume that iodine is our limiting reagent, so negative 0.72 here. Negative 0.72 times by our molar ratio, 2 aluminums over 3 iodines. And then add 0.72 here times by our molar ratio, 2 aluminum iodides over 3 iodines. So now we do 0.5 minus 0.72 times by 2/3 gives us 0.02 moles. 0 moles here. And then when we take our 0.72 times by 2 divided by 3, we get 0.48 moles here. So what this shows us is that we have this much aluminum remaining at the end. We've used up all our iodine because it was our limiting reagent, and then we produce 0.48 moles of aluminum iodide. Okay, that's it for this video. We'll talk about Le Chatelier's principle in a further video. Bye, y'all.